Okay, so I think we're at example 17.11, and this is finding the hydroxide ion concentration of a strong base solution. Okay, and so you'll remember that the pH scale goes from about 1 to about 14, with 7 being right in the middle. And in the range of pH 1 to 7, we are acidic, where the H plus concentration would be the dominant factor, okay? And in the 7 to 14 range, we are basic, where the hydroxide ion concentration would be the dominant factor. And remember that a Bronsted-Lowry acid increases the H plus concentration and serves to make things acidic, and a Bronsted-Lowry base increases the hydroxide ion concentration and serves to make things basic. Also remember that the H plus concentration is equal to the H3O plus concentration. In other words, those are the same thing, so we use those interchangeably. The more correct thing to say is H3O plus, because H pluses don't exist by themselves. They're always hydrated or surrounded by water, but often H plus is used just to abbreviate things, and I may use H plus today, so don't get confused there. All right, so we've spent some time finding the H plus concentration, and we learned that the pH is equal to the negative log of the H plus concentration. And remember, that's the same as the H3O plus concentration. Okay, and we have another term called POH, which is equal to the negative log of the hydroxide ion concentration. And we use the pH when we're in the acidic range in general, and we use the POH when we're in the basic range in general. Also, you might remember that the H3O plus concentration, or let me back up again. I'm trying to do a little bit of reviewing here so we won't leave anybody behind. That in aqueous solution, there's always the autoionization of water, where water reacts with itself to form H3O plus plus OH minus, and that's called the autoionization of water. And that isn't normally important until you get into the pH 7 range, where you have to actually consider that. But because of the autoionization of water, if we draw the K for that reaction, okay, we can write that as H3O plus times OH minus is 1 times 10 to the minus 14. Okay, and we could do some derivations there that will show us if we solve for H3O plus, okay, and then if we solve for OH minus, we can get another relationship. We can relate that to the pH. In other words, the pH plus the POH is equal to 14. Okay, so keeping all of these relationships in mind, we're going to work some problems. Okay, so let's back up and look at all of these relationships again. So the pH is equal to the negative log of the H plus concentration. That's generally the form that we're going to use if we're in the 1 to 7 range. The POH is the negative log of the hydroxide ion concentration. That's the form we're generally going to use if we're in the 7 to 14 range, okay? We also can calculate one from the other, because due to the autoionization of water, we have this relationship where the hydronium ion concentration and the hydroxide ion concentration are in a constant equilibrium, where the Kw is going to be equal to 1 times 10 to the minus 14. So if you know one of those species, you can calculate the other. And from those relationships, we can determine that the pH plus the POH is equal to 14. So you might want to write down all of the relationships that I've just highlighted and put those on a formula chart, okay, because those are important. All right, so the question here asks us, and as I said before, I wasn't going to work all of the example problems, but I think I'll work through this one because we can work it in a couple of different ways. So this question says, determine the hydroxide ion concentration and the pH in each of these solutions. Now, we were told from the title of the problem that each of these solutions is a strong base solution. And we learned earlier in the chapter that a strong base, by definition, is a species that completely dissociates when it's put into water. So this one on the left, A, is potassium hydroxide. So if you put it into water, potassium hydroxide is going to dissociate into K plus OH minus ions in water. That's why we have these little AQs. Okay, I often leave those AQs off because I'm kind of lazy, but potassium hydroxide dissociates in water to K plus and OH minus. Okay, and we were told that the molar concentration for this species is 0.225 molar for potassium hydroxide. So if we write the balanced equation for the dissociation of potassium hydroxide, we learn that 1 mole of potassium hydroxide dissociates into 1 mole of K plus ions and 1 mole of OH minus ions, okay? So we know that our hydroxide ion concentration is going to be equal to 0.225 molar because we have a 1-to-1 relationship, and we started with 0.225 molar of potassium hydroxide initially. Now, there are a couple of ways to solve part B. So we found the hydroxide ion concentration because it was just the same in this case as the concentration of what we started with, because we have this 1-to-1 relationship in the balanced equation. So part A is done. Okay. So part A is to determine the hydroxide ion concentration, and part B is determine the pH. Remember, the pH is equal to the negative log of the H plus concentration. Okay, so there's a couple of different ways that we can work that problem. One of the ways is to say that I know that the H3O plus concentration times the OH minus concentration is always going to equal 1 times 10 to the minus 14, because that's our Kw for that reaction, or that's Kw, which means the K for the ionization of water. Okay, so you can plug in that hydroxide ion concentration, which is 0.225, and the Kw, let me erase this, which is 1 times 10 to the minus 14, and then you can solve for H3O plus, okay, which in this case is 4.44 times 10 to the minus 14, and plug that into the equation for pH, which we just noted pH is equal to the negative log of the H plus. So when you do that, pH is equal to negative log of 4.44 times 10 to the minus 14, which gives you 13.35, which makes sense because it's above 7. So you're going to be in the basic range here. Now let's look at another way to solve this problem, okay? So 0.225 molar potassium hydroxide, we write the equation for the ionization of potassium hydroxide in water. Potassium hydroxide, it goes to K plus and OH minus. So we learned that our hydroxide ion concentration is 0.225 molar. Okay, so instead of going through all of this, you can just say the POH is equal to the negative log, which I think is a little bit quicker, of the hydroxide ion concentration. Okay, so the POH is equal to, and I didn't work this problem out, so I'm going to go ahead and do it on my calculator here. The negative log of hydroxide is 0.225. So I just took this straight from the problem. Okay, so it makes it a little bit shorter. Not much in this case, but in some cases it'll actually be a lot shorter. 0.225 on my calculator, and then I pushed log and then the negative of that. So the POH is equal to 0.648. Okay, I'll just write that. So this is my significant figure Anyway, so we'll get that in a minute. All right, so the pOH is equal to this. So remember, the pH plus the pOH is equal to 14. Okay, and so if I subtract, so I say pH plus pOH equals 14. So the pH is equal to 14 minus, I can't get this stupid computer to write, minus pOH, right? Okay, so that's going to be equal to 14 minus 0.648, which is equal to, so I just take my calculator, I just put in plus 14 here because I already had the negative 0.648, and that gives me 13.352. So all I had to do to solve this problem very, very quickly, okay, let's recap here, and hopefully you're understanding what I'm saying here, is I put the 0.225 I was given into the calculator, then I hit the log button, okay, and then I hit plus 14 and I got the answer. Okay, so this is very, very simple and very much quicker than writing all this crap out over here. Okay, so there's two different ways to solve this problem. I can use the formula for the KW, which says that H3O plus times 8 times OH minus gives you 1 times 10 to the minus 14. I can solve for H3O plus and then take the negative log of that, or I can just use what I know, and that is pOH plus pH is equal to 14. Take that 0.225, hit the log of it, and that's going to be giving me a negative of what I need, and then I just add that to 14 and get the answer. So that was a lot simpler. Hopefully you can see what I did. Now let's solve part B of the problem, which says 0.0015 molar strontium hydroxide solution. Okay, and so let me just run down to where I have this. Okay, I'm just going to use what I've got here. Okay, so strontium hydroxide is also, we were told, a strong base. So 1 mole of strontium hydroxide completely dissociates into 1 mole of Sr2 plus and 2 moles of OH minus, okay? So from the balanced equation, I see that I get 2 moles of hydroxide for every 1 mole of strontium hydroxide I put in, and my concentration is 0.0015, so my hydroxide ion concentration is equal to 2 times that. So my hydroxide ion concentration is 0.0030. Okay, so if you wanted to use the first method to do this, you could solve for H3O plus concentration by plugging in that 0.0030 into this formula for KW. Okay, and then you can take the negative log of that, giving you the pH is 11.48, or you can work it like this. I can say pOH is equal to negative log of 0.0030, which is my OH minus concentration. Okay, so I didn't work this out yet, so I'm just going to put that in my calculator. So 0.0030, and I'm going to take the log of that, and that gives me negative 2.52. So the negative log of that would be 2.52. So my pOH, I'll just go ahead and write it down, is equal to 2.52. Okay, so the pH plus pOH is equal to 14. All right, and so the pH is equal to 14. I can't read this stupid thing to write. Minus 2.52. Okay, so I'll say plus 14 on my calculator, and that gives me 11.47 in like a few keystrokes on my calculator. Okay, that's 11.48. I'm sorry, because I round up. Okay, so I got the exact same answer with a lot easier way to work this problem. Okay, so let's work the 4 practice problems. Hopefully you can see what I just did there. Working the 4 practice problem, 4 practice 17.11. I don't even see it on here. Let me see. All right, and so, and see, the study guide actually worked it according to the way I just did it. Find the hydroxide ion concentration and the pH of a 0.010 molar barium hydroxide solution. Ugh, I didn't write that right. Hydroxide solution, okay? So let's write the formula for the dissociation of barium hydroxide in water. So BaOH2, and this is all AQ, which I'm going to pretty much leave off, but I'll put it on this one, goes to Ba2 plus, and that's AQ, okay, plus 2OH minus, and that's AQ. Okay, so we got the 2OH minus here because of this 2 here. Okay, we got 2 OHs associated with our barium. Okay, and that's because OH minus has a -1 charge and barium has a +2 charge. Okay, all right, and so that's our balanced equation, and so we know that we're going to get 2 moles of hydroxide for every 1 mole of barium. So the hydroxide ion concentration is equal to, let me change my color here so everybody can see it, 2 times 0.010 molar, and that is equal to 0.020. I hate this tablet. I'm so sorry. Molar, okay? So that's our hydroxide ion concentration. So the pH is equal to 14 minus the pOH, okay? And that is equal to 14 minus the negative log of the OH minus concentration, which is equal to 14 minus, well, I could say 14 plus the log of 0.020, which is equal to 12.30. Okay, so that's my pH. So all you have to do, if you have a calculator like mine, is put 0.020 in the calculator, hit the log button, and hit plus 14, and you've got your answer. So pretty simple to work that problem. All right, so for the strong bases, we know that they completely dissociate in water, and the same thing for strong acids. So finding the pH for those is very straightforward. All you have to do is take the negative log of the concentration of either the H plus or the OH minus, and you can directly calculate the pH from that. Okay, but if you have a weak base solution, remember that you've set up an equilibrium where your weak base is, you have to worry about both the forward and the reverse reaction. So for this strong base solution, your arrow actually only goes one way. Essentially, you don't really get any of the reverse reaction products. Okay, so the reverse reaction is negligible. You don't have to worry about it. But if you have this weak base solution, then you have an equilibrium that is set up such that you have to worry about the products going back and forming reactants. And so then you get a K for that reaction. And so what you have to do is set everything up and set it equal to that K, just like we've been doing all along. So this is the same kind of problem that we've been doing, but you just have to kind of understand what's going on so that you know how to work the problem, okay? So in order to find the pH, okay, so it asked us here to find the hydroxide ion concentration, okay, which we can get from setting up our equilibrium problem. All right, so we're going to use an ice table for that. And it asked us to find the pH, okay, which we can get, as we saw, from the hydroxide ion concentration, because pH plus pOH is equal to 14, okay? So remember, pH is equal to the negative log of the H plus concentration, and pH plus pOH is equal to 14. Okay, so we're going to be looking for the hydroxide ion concentration here, but we need the H plus concentration to calculate the pH. And so we can get the hydroxide ion concentration from setting up this equilibrium expression. So in order to set up our ice table, the first thing we do is write the equation for the ionization. So if you put ammonia, this is NH3, in water, okay, then you get NH4 plus OH minus. Okay, so that's your equilibrium. That's your equilibrium expression here. This is a reversible reaction, so it goes both ways. So we could set up an ice table. So we could just ignore the water because that's a liquid. So we only have to worry about the ammonia forming NH4 plus and OH minus. So this is a weak base because it increases the hydroxide ion concentration in water, and it's a weak base because it doesn't completely dissociate in water. We have some ammonia that's left, okay? All right, and so we set that up as our starting material is the NH3, and our products are NH4 plus and OH minus, and initially we have a 0.1 molar solution of ammonia, okay? So then we represent the change, we represent the loss due to ionization as minus X from the ammonia. And so if we lose 1 mole of X from ammonia, that amount is going to be gained in NH4 plus and OH minus. So again, I'm going to run through this one with the example, and then I'll work the four practice problem for you. Okay? So I've left room to work through the problem, but we just don't have time to do all these. Okay? So now we can say that the ammonia concentration at equilibrium is 0.100 minus X. Ammonium, that's the NH4 plus, is X, and hydroxide is X. So we can set up our K expression, which in this case is going to be Kb for ammonia, which you can you should be able to look up on a chart. If you don't know the Kb, then you can calculate it. So we're going to be doing some of that in a little while. So Kb is equal to NH4 plus times OH minus over NH3. So that's the way we set up our equilibrium expression. So we can set up at equilibrium, we know that we have X times X over 0.100 minus X because it's products over reactants. Okay, so that gives us X squared over 0.100 minus X. So if we assume that X is small and X is pretty close to 0, then we can say our Kb is equal to X squared over 0.100. Okay, so Kb is 1.76. We got that from table 17.8 times 10 to the minus 5th is equal to X squared over 0.100. So we could take the square root of both sides and solve for X, and we get X is equal to 1.33 times 10 to the minus 3rd. If we want to check that our X is small approximation was valid, remember that we really need to say that what we're subtracting is going to be, or rather our concentration is more than 3 orders of magnitude away from, in general, if your concentration is more than 3 orders of magnitude away from your K, then you can pretty much assume that your X, a small approximation, is valid. But if you want to check that, what you do is have to take the thing that you subtracted, which is going to be the X here, divided by the concentration, multiply times 100, so that's part over the whole times 100, and that's going to give you 1.33%. So if it's less than 5%, it's valid, and that's the only reason that we work this little part here. All right, so we determined that the hydroxide ion concentration is 1.33 times 10 to the minus 3rd, and that was because X was equal to the hydroxide ion concentration. Okay, and so 1.33 times 10 to the minus 3rd, and then we can solve for the H3O plus concentration, or we can just take the P, we can take the negative log of that and say it's the POH and do it the other way, but in this case they just used H3O plus times OH minus, plugging in 1.33 times 10 to the minus third is equal to Kw, and solve for that. That gives you 7.52 times 10 to the minus 12 for the hydronium ion concentration. Now remember, we were supposed to find the hydroxide ion concentration, which we found, okay? And then we need the pH. The pH is not the hydroxide ion concentration. It's going to be the negative log of the H plus concentration, so we need to solve for that. So we solved for the H plus concentration. We take the negative log of that to get the pH. So that gives us negative log of 7.52 times 10 to the minus 12. That gives us a pH of 11.124, which makes sense because this was a basic solution. We're in that 7 to 14 range, okay? Now the for practice 17.12, I'll go ahead and work that one to give you an example of how to do this. All right, find the hydroxide ion concentration and the pH of a 0.33 molar methylamine solution. So what you'll need to do is look up methylamine in a table and find out if that is a strong base or a weak base, okay? Because we weren't told here. Then, if it's a weak base, we're going to find the Kb in a table. Now, if we don't have the Kb, we'll learn to solve for that later on. Okay, and so that is in table 17.8, which I don't actually have here, but I think I have it. If we need it, we'll look it up later. So 17.8, okay, if you look, you're going to look that up. We see that that's a weak base, so we know we have to set up an equilibrium problem. In order to solve this problem, okay? Now, so let's write our equation for our equilibrium problem, okay? And then next, what we're going to do is solve for the hydroxide ion concentration, which we're going to find from this equilibrium problem because bases increase the hydroxide ion concentration in solution. And then we're going to use that hydroxide ion concentration to solve for pH. pH, okay? So we need to find the hydroxide ion concentration and the pH. That's what we were asked to do in this problem, okay? So let's write our equilibrium expression here. I'll go ahead and do that. So CH3 NH2, that's methylamine, plus H2O. And remember, H2O is a liquid. Everything else is AQ. This is a reversible reaction because it's a equilibrium reaction. Is forming CH3NH3 plus. And if you don't know how to do that, and I really honestly wouldn't expect you to, you can do a couple of things. First of all, you can look it up. And second, you can think about it. What's happening here, remember, is that bases increase the hydroxide ion concentration, okay? And they do that either by dissociating or they can pull off a hydrogen from water, okay? So if this base pulls off a hydrogen from water, it's going to have an extra hydrogen on it. So it went from NH2 to NH3 plus, okay? And OH minus in order to keep our charges balanced, okay? So now we're going to set up an ice table. I think I'll change colors for that. All right, so we're going to draw a double line between starting materials and products. We're going to draw initial, change, equilibrium here. All right, we don't have to worry about the water because it is a liquid, so it's a pure substance. We don't worry about it in the ice table, okay? So our methylamine, we started out with 0.33. We're going to lose X of that, okay? And we're going to gain X of that over here. And that's because of our 1-to-1 ratio in the equilibrium expression. So we started out with 0 of this and essentially 0 of this. Now there's always a little bit of hydroxide due to the autoionization of water, but in this case our methylamine concentration is large enough that we can just ignore that, okay? So we end up with 0.33 minus X at equilibrium for methylamine, and X for the other two species. So let's go down and set up our K expression. So KB, this is a KB because we have the base. Methylamine is a base. And we need to set up the K expression because it's an equilibrium problem because it's a weak base. It doesn't completely dissociate in water. Is equal to the concentration of CH3 NH3 plus methylammonium times hydroxide divided by CH3NH2. So that's product over reactants, and we don't worry about the water because it's a liquid. Okay, so we can look up the KB in a table. 4.4 times 10 to the minus fourth is equal to X squared, okay, because that's X times X here, okay, over 0.33 minus X. Now this problem would be hard to work if we didn't make the X is small approximation. So we're going to say that X is small, so X is essentially 0. So solving for X, we can say that I'm just going to go ahead and multiply both sides by 0.33. We can say that 0.33 times 4.4 times 10 to the minus fourth is equal to X squared, okay? So X is equal to the square root of 0.33 times 4.4 times 10 to the minus fourth. Okay, that's equal to 0.01205. Okay. Now I know that X was that, and that's also equal to the hydroxide ion concentration. Okay, and my sig figs are at 2. Okay, because I got 2 sig figs. So that's so I'm going to just draw a line under that for sig figs. Okay. So I could do this a couple of different ways. I could either say that hydroxide ion concentration times hydronium ion concentration is equal to Kw, or I can just find the POH is equal to negative log of the hydroxide ion concentration, which is equal to negative log of the 0.01205, which is equal to, and I didn't do it that way, so I'm going to have to do it, 0.01205 log is equal to 1.919. Okay, and then to find the pH, I just say 14 minus POH is equal to 14 minus 1.9190, which is equal to, I just put in plus 14 in my calculator, 12.08. Okay, so the study guide goes through and works it the other way, saying that hydroxide ion times hydronium ion is 1 times 10 to the minus 14, solves for hydroxide, and then calculates pH, which takes a little bit longer. So you could do it either way. So I've shown you both ways. Okay, so we have 17 problems in this chapter. So moving on, I wanted to go ahead and go back to the PowerPoints. Okay, so I'm going to try to run through these as quickly as possible because I would like to finish this chapter today. So I have, let me see, 4 more problems, I think. I've got one. I just got a couple more math problems, maybe one more math problem. So hopefully we'll finish this today. All right, so quickly moving on. H3O plus and present ionization. I think we talked about this last time. So the hydronium ion concentration of a weak acid increases with increasing acid concentration. Okay, but the percent ionization decreases with increasing acid concentration. So let's look at what that's actually trying to say. It's trying to say, let me think a minute. So let's say that acetic acid, which is, I know acetic acid is this, CH3COOH. How do they draw it? HC2H3O2. That's the way your book draws it. Okay, acetic acid in water, I'll leave the water out, goes to H plus C2H3O2 minus, okay? So that's an equilibrium problem because we just saw that that's a weak acid. Okay, so we get some forward reaction and we get some reverse reaction at equilibrium. So remember, because of Le Chatelier's principle, if we add in more of the acetate, it's going to drive it back in the reverse direction. And if we add in more of the H plus, it's going to drive it back in the reverse direction. So adding more product drives it in the reverse direction. So percent ionization, in other words, the percent that's ionized here, the percent of products forming, is going to decrease with increasing acid concentration. Okay? So even though you may have more acid, your percent ionization is going to decrease, okay? So which weak acid has the greatest percent ionization? So it's going to be the one with the smaller acid concentration due to the Le Chatelier's principle. So we'll look at some problems with that, I think, later on. I'm going to move on from there. Finding the pH of mixtures of acids. Now that's kind of a problem. What if you have a mixture of acids? And we're going to be looking at this a lot more in the next chapter. For a mixture of a strong acid with a weak acid, the complete ionization of strong acid, okay, is going to provide more than enough H3O plus to shift the weak acid equilibrium to the left. In other words, according to Le Chatelier's principle, when you add a strong acid in, you're going to, so adding more of this H plus, it's going to shift the ionization so far to the left that your percent ionization for your weak acid is going to be low. So if you have something like sulfuric, let's say HCl, hydrochloric acid, and you put that in with the acetic acid, okay, you put those in together, this is a strong acid, so you're going to get all H plus plus Cl minus. You're going to have so much H plus hanging around that it's going to shift the dissociation of the weak acid back in the reverse direction, back towards starting materials. So you don't even need to consider the weak acid at all if you have a weak acid and a strong acid in solution in general, unless your strong acid concentration is very, very low. You generally only need to consider only the strong acid, okay? So then you just consider the pH from the strong acid. So which solution is most acidic? That is, has the lowest pH. 1 molar HCl or 2 molar HF, or a solution that is 1 molar in HF and 1 molar in hypochlorous acid, which is another weak acid. So the 1 molar HCl is more acidic and has a lower pH. I don't even know how you would determine that from this information, because you're not given the Kas or anything. But anyway, I mean, generally, because this is opposing trends here. But anyway, what they're saying here is that you have a weak acid, and that's going to have a higher pH than a strong acid in general, even if you have double the concentration. I don't really see how that's that relatable to their point. But anyway. All right, so looking at strong bases, the stronger the base, the more willing it is to accept H plus. Okay, or in other words, strong bases, you can also say completely dissociate in water. So for ionic bases like sodium hydroxide, they completely dissociate in water essentially, and they're strong electrolytes. And so you can just say that the POH is equal to the hydroxide ion concentration, which is equal to the concentration of the base that you put in. So you can assume that, and we just did some problems with that. Weak bases only accept a small fraction of molecules of H+, okay, and they increase the hydroxide ion concentration in water, but you have to set up an equilibrium problem in order to find out what your ionization is, and that's going to be dependent on your ionization constant, which we just worked some problems with. So here's some common weak bases. You might want to refer to this chart later on. We have carbonate, methylamine, ethylamine, ammonia, bicarbonate, pyridine, and aniline. Okay, so you have some KBs for them. In other words, how well do they dissociate? So the higher the number, the better the dissociation in water. So this is going from stronger to weaker. Okay, so amines are bases because they have this lone pair, and I got to run through this stuff real fast. I'm sorry I'm going so fast, but I need to move forward. Amines are bases because they have this lone pair that is available to pick up a hydrogen. So this is a nitrogen. This blue is a nitrogen, and it has a lone pair that's going to be able to pick up a hydrogen and form a positively charged species. And they're very good at doing that, okay? So they're often used in reactions to do that. Okay, so if you want to find the hydroxide ion concentration of a weak base, you need to set up an ice table. We just worked some problems from that, so I'm not going to spend up a lot of time on that. The next topic is acids and base properties of ions and salts. Okay, so you need to consider whether if you have a salt solution, if you make a pure salt solution, sometimes a salt solution might not necessarily be neutral. So we generally think of salt solutions as being like pH 7, and if you dissolve something like sodium chloride into water, you're going to get a solution that's neutral. And we'll learn why that is in just a minute. But some salt solutions actually come out to be basic or acidic, and that's because some of the anions or cations can actually act as acids or bases. So remember, we had conjugate bases and conjugate acids. So we had conjugate bases of acids and conjugate acids of bases. Well, it turns out if you just put in the conjugate base in the form of a salt, you can form an acidic solution. And if you just put in the conjugate acid in the form of a salt, you can form a basic solution. So the cation of a weak base will ionize in water and affect the pH of the solution. So sodium bicarbonate solutions are basic because sodium is the cation of the strong base, sodium hydroxide. Carbonate is the conjugate base of the weak acid, carbonic acid. Okay, so because the sodium part is neutral, the conjugate base of the weak acid is going to form a basic solution. So the anions that are anions of bases, so the conjugate bases of acids form basic solutions. Cations tend to form acidic solutions if they're the conjugate acid of a base, okay? So anions tend to form basic or neutral solutions. Cations tend to form acidic or neutral solutions. So in other words, what they're talking about here, this is poorly worded because all anions have to have an associated cation and vice versa. Sorry, I think I'm allergic to something in my house right now. Somebody let the cat in earlier. All right, so if it's the conjugate base of a acid, it's going to form a basic solution. If it's the conjugate acid of a base, it's going to form an acidic solution. So let's look at what that means. So every anion can be thought of a conjugate base of an acid, therefore every anion can potentially be a base. Now remember, this F thing is just something that my screen is doing here. Okay. So so we have this A minus plus H2O gives us HA plus OH minus. The stronger the acid, the weaker the conjugate base. That we learned that earlier. So an anion that is the conjugate base of a strong acid, since strong acids completely dissociate, okay, so let's say we had H plus Cl minus from HCl, that's going to, oh, what was I doing? That's backwards. I was thinking about this backwards. Sorry, guys. But they wrote it backwards, so it got me mixed up. So let's recap here. So we're saying that HCl, that's a strong acid, is going to completely dissociate in water into H plus Cl minus. Okay, so it completely dissociates. So that means that it's not going to want to go back in the other direction. So if you had just the H plus Cl minus, okay, it's not going to want to add to water to form HCl and OH minus. It's not going to happen. So if you just had that chloride in solution, since this reaction arrow is essentially one way, if you put the chloride in solution instead of the HCl, let's say we had sodium chloride, let's say we had Na, oh my gosh, I don't know what happened there. Let's say we had NaCl, okay? Then that chloride is the conjugate base of the strong acid HCl. It's not going to want to pull off a hydrogen from water and form hydroxide ions. That's just not going to happen, okay? Because HCl, this reaction is essentially only toward dissociation. So the anions of strong acids, the conjugate bases of strong acids, are going to be pH neutral. So if you put sodium chloride into water, you're going to get my computer's acting up. You're going to get a pH neutral solution, okay? But if you have an anion that's a conjugate base of a weak acid, so let's look at that. So let's say that HF, okay, you put hydrofluoric acid, that's a weak acid in water, it's going to form H plus F minus, okay, F minus. Then this is a two-way arrow because this is a weak acid. So if you just put F minus in solution with some counterion like sodium, the sodium is neutral, okay, but the F minus is going to want to react with your water to form HF plus OH minus, okay, and so that's going to give you the conjugate base of a weak acid. That's going to increase your hydroxide ion concentration and give you a basic solution, okay? So the strength of conjugate acid-base pairs, the stronger the acid, the weaker the conjugate base, okay? So this is weak, this is strong, this is strong, and this is weak, okay? So the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid, okay? So strong acids form pH neutral solutions as I'm sorry, no. The conjugate bases of strong acids form pH neutral solutions, and the conjugate acids of strong bases tend to form pH neutral solutions as well. I don't think that's really, I don't think these are the examples I wanted to use though for the bases. So let's not worry about the bases on this one, okay? So you have to consider the ionization if you're looking at whether something's going to affect and become a acid or a base. So if, in other words, okay, so let's recap here. If you, I gotta move on to working problems in a minute. If you put a strong acid in solution, it completely dissociates. So the conjugate bases of those strong acids are going to be pH neutral. If you put a strong base in solution, it's going to completely dissociate. So the conjugate bases are going to tend to be, or the cations there are going to tend to be pH neutral. So you've got to think about what you have in order to figure out whether they're neutral or not. Okay, so a lot of times reference books are only going to give you the Ka values instead of the Kb values because you can calculate Kb from Ka. So we talked about that already. And that's because if you set up the equilibrium expression, you can say that a Ka is equal to H3O plus times A minus over HA, and Kb is equal to OH times HA over A minus. So if you multiply Ka times Kb, you can see that you get H3O plus times OH minus, because everything else cancels out, is equal to Kw. So if you know your Kb, Ka, you can get the Kb from the Kw. Okay, so we're going to work some problems with that. So Kw is equal to Ka times Kb. Okay, So if you know your K, let me write that down. KW equals KA times KB. So KB is equal to KW over KA. So you can solve for your KB if you know your KA. So which anion acts as a weak base? Okay, so remember HCl is a strong acid. HBr is a strong acid. FHF is a weak acid. So the F minus anion is going to act as a weak base. Okay, so the stronger the base, the weaker the conjugate acid. We talked about that already. Okay, so the cation is the counterion of a strong base, and that's going to be pH neutral. All right, so a strong base like sodium hydroxide, if you put that into solution, it's going to dissociate in Na plus OH minus. Okay, so hydroxide is always going to increase the hydroxide ion concentration, but the cation here is the conjugate acid of that strong base. Okay, and so that's not going to want to pick up hydrogen at all. Okay, conjugate acid. I'm sorry, it's not going to want. It's not going to want to. It can't increase the hydrogen ion concentration. I'm sorry. So it is. I am totally phrasing this wrong. Okay, the cation is not able to increase the hydrogen ion concentration. So the cation, counterion of a weak base, is pH neutral. All right, so the cation of a strong base is pH neutral. The cation of a weak base is going to be weakly acidic. So remember that NH3 goes to, and this is reversible, NH4 plus OH minus. So the cation here is weakly acidic because it can actually increase the H plus concentration in solution. Okay, so if you look at the reverse reaction, then the NH4 plus H2O goes to NH3 plus H3O plus. We're increasing the H3O plus concentration in solution. If you use something like ammonium chloride. Okay, so if you put a salt like ammonium chloride in solution, that solution is going to be weakly acidic because the ammonium is a conjugate acid of a weak base. Okay. Another thing that's weakly acidic is cations that are highly charged small metal ions, and that is because the alkali metal cations and alkali metal earth cations are these are pH neutral, but you can actually form an acid if you put something like aluminum in solution, and so these actually become hydrated and increase the H plus concentration. Okay, so we'll look at some examples of this, classifying these things. I don't want to read all this crap. All right, so here is a chart you can use. If the cation is the conjugate acid of a weak base and the anion is the conjugate base of a strong acid, you get an acidic solution. If the cation is a conjugate acid of a weak base and the anion is the conjugate base of a weak acid, then you have to consider the relative strengths. If the cation is a small, highly charged metal ion like aluminum, and the anion is the anion is the conjugate base of a strong acid, then you get an acidic solution. Or if it's the conjugate base of a weak acid, then you have to look at the relative strengths, and we'll look at some examples of that in a minute. All right, if the cation is a counterion of a strong base, and the anion is a conjugate base of a strong acid, then you get a neutral solution. Or if it's a conjugate base of a weak acid, then it becomes basic. So let's look at some examples here. Which ionic compound forms when an acidic solution is dissolved in water? Which ionic compound forms an acidic solution when dissolved in water? Okay, so which of these forms an acidic solution? Okay, so let's look at this. So sodium bicarbonate, we have sodium is the cation from, and so it's going to be pH neutral, because you can think of like sodium chloride is a neutral salt. Bicarbonate is actually a weak acid, okay? And so, let me write that down. Carbonic acid is a weak acid. So, if you put the carbonate ion in solution, it can actually form a basic solution because it will actually pick up a hydrogen from water and increase the hydroxide ion concentration. And I meant to write that like that. Okay, so this sodium bicarbonate is actually going to act as a base, because the bicarbonate, which is this HCO3, is the conjugate base of a weak acid. So it can actually act as a base if you put it in solution. KCl is a salt where if you think of HCl and you put that in water, that's going to completely dissociate because it's the strong acid. So the chloride is a conjugate base of a strong acid. So if you use KCl, that's going to completely dissociate in water. So you're not going to get any acidic or basic solution. Okay. Ammonium bromide, ammonia, NH3, okay, dissociates to NH4 plus OH minus. So ammonia is a weak base. So if you put the ammonium ion in solution, NH4 plus Br minus, then you're going to be, we don't have anything to form hydroxide here. So what we're doing is that's going to actually lose a hydrogen to water, okay, and form H3O plus Br minus plus NH3, right? Yeah. So that's going to actually form a weakly acidic solution, okay, because it is the conjugate base of a weak acid. Okay, so I need to start working problems. Let me go ahead and run through this real quick. If you have a polyprotic acid in general, that means that you've got an acid that can dissociate in steps. So let's look at a polyprotic acid. Let's look at some examples here. So that could be like sulfuric acid, oxalic acid, sulfurous acid, phosphoric acid, and here's some more of them. So everything in red, these are all acidic hydrogens. So these hydrogens come off in steps, because when you remove the first hydrogen, you're going to have a negative charge on that molecule. It's going to be hard to remove the second hydrogen because increasing the charge on the molecule is going to get harder and harder. So the first Ka1 for these acids is going to tend to be much, much larger than the Ka2 versus the Ka3, okay? So in general, when you have the first ionization, you can generally just consider the Ka1 when you do these problems. You generally don't need to consider the Ka2 or the Ka3, except for the case of sulfuric acid, because sulfuric acid is a strong acid and the Ka2 is very large. Okay, this is 1 times 10 to the minus 1.2 times 10 to the minus 2. Since it's so large, you have to consider the second Ka, but not but I'm sorry, the second Ka when you're working these problems. So we're going to go ahead and work some problems with this. And I think that's all that I'm going to talk about in these tables, because I got to move on. Okay. All right. So 17.13, let's see if we can work through these problems, because I've botched enough stuff today. All right. Classify each anion as a weak base or pH neutral. Okay, so we've learned that our anions can act as weak bases or they can be pH neutral. From 17.3, you can see that nitrate is the conjugate base of a strong acid, nitric acid, and therefore if you put something with a nitrate in it in solution, like sodium nitrate, it's going to be pH neutral. And if the cation is pH neutral also. Okay, so from table 17.5 for HNO2, for NO2, you learned that NO2 minus is the conjugate base of a weak acid. This is nitrous acid and is therefore a weak base. Okay, so from table 17.5, you know that acetate is the conjugate base of a weak acid, acetic acid, and therefore a weak base. So if you put something like sodium acetate in solution, you're going to be forming a weakly basic solution. All right, so for 17.13, classify each anion as a weak base or pH neutral. CHO2 minus, that's formate. Okay, so from table 17.5, you know that formate is the conjugate base of a weak acid, and therefore it is a weak base because it's the conjugate base of formic acid. ClO4 minus, from table 17.3, you see that ClO4 minus is the conjugate base of a strong acid, HClO4, and is therefore pH neutral. Okay, this is perchloric acid. So this is perchlorate. All right. So 17.14, this is our last math problem, and I hope I can get my computer to cooperate with me long enough to work this math problem. Okay. I think it's our last math problem. Determine the pH of a solution containing an anion acting as a base. Find the pH of a 0.1 molar sodium formate solution. The salt completely dissociates into Na plus and CHO2 minus, and the Na plus ion has no acid or base properties. Okay. All right. So since the sodium ion does not have any acidic or basic properties, you could ignore it. Write the balanced equation for the ionization of water by the basic anion and use it to prepare an ice table. So what we're saying here is the sodium formate, you can ignore the sodium and you have to only consider the CHO2 minus, and since it's the conjugate base of a weak acid, it's going to act as a base. Okay, so since it's acting as a base, you have to set up the K expression. So we're going to set up this KB expression for formate, where formate dissociates into in water, it forms formic acid and OH minus. So our initial concentration is going to be the initial concentration of the sodium formate, because we got a 1-to-1 ratio here. Okay, and we have 0 of the formic acid and 0 of hydroxide in the beginning, because you can assume that you ignore the autoionization of water. All right, and so then we write our equilibrium, our ice table, minus x plus x and plus x. Then at equilibrium, we're going to have 0.100 minus x, and then x and x. Okay, so we can set up the equilibrium expression. Kb is equal to the HCO2, so formic acid times hydroxide over formate. And so that gives us Kb is equal to x squared over 0.1 minus x. Now we need Kb, and we don't have Kb from a table, so we learned that Kb is equal to Kw over Ka, okay, which is 1 times 10 to the minus 14 over 1.8 times 10 to the minus 4th. So we get this 5.6 times 10 to the minus 11. So we can put that in for Kb here, and we can assume that x is small. So that gives us the Kb 5.6 times 10 to the minus 11, and we've done these kind of problems over and over, is equal to x squared over 0.100. So now you just multiply both sides by 0.100 and take the square root. Okay, so that gives us x is equal to 2.4 times 10 to the minus 6, and that is going to be our hydroxide ion concentration. Okay, so confirm that the x is small approximation is valid. So the problem says find the pH of this solution. So that's just a confirmation there. So the hydroxide ion concentration is equal to 2.4 times 10 to the minus 6. So you can either find the POH or you can solve it like this. H3O plus times OH minus equals KW. And so you solve for H3O plus, which gives you 4.2 times 10 to the minus 9. And we're going to work the 4 practice problem, guys. So that's pH is equal to negative log of H3O plus is equal to negative log of 4.2 times 10 to the minus 9 is equal to 8.38. Okay, which makes sense because we're working a basic problem. So the 4 practice problem says find the pH of a 0.250 molar sodium acetate solution. So we learned that the acetic acid HC2H3O2 is a weak acid. So we can set up an equilibrium problem for that, which gives us H plus C2H3O2 minus. Okay, so this reaction goes in both directions. So if I take just the acetate anion and I put that into solution, so that's what I've done here because I got sodium acetate. This is not an acid, this is a salt solution. So I can say that, so I can write an equilibrium expression for that. If I put that acetate in solution, I'm going to have NaC2H3O2 goes to, okay, I gotta find my problem here. Okay, goes to, and I could say plus H3O plus, plus H2O, goes to OH minus plus HC to H3O2, okay? So what they're saying is if I put just the anion in solution in the form of its salt, I don't have any of the H plus here. I don't have the H plus. I'm not increasing the H plus concentration. What I'm going to do then is when this reacts with water, this is going to react with water, okay? It's going to act as a base and pull a hydrogen off of water, giving me OH minus plus the acid, because this is an equilibrium problem, because this is a reversible reaction. So now I can set up an ice table, okay? I can set up an ice table. So I started out with 0.250 moles of this. I've got a 1-to-1 ratio, so I've got 0 of this and approximately 0 of this, and I've got 0 of this, right? So I've got minus x plus x plus x, okay? And then I've got 0.250 minus x, and this is x, and this is x. So I can set up a KB expression where I can say that KB, because this is a base, not an acid, is equal to HC2, I keep doing that, HC2, H3O2, my computer is not writing anymore, times OH minus, I think it's overheating or something, over C2H3O2 minus, all right, and that, so I got to solve for KB because I don't know KB, so I can get KB from Ka, okay? So I can say Ka times KB equals KW. So KB is equal to KW over Ka. We're going to be doing this a lot in the next chapter too. Which is equal to 1 times 10 to the minus 14 over the Ka, which is 1 times 10 to the minus 5th, and that is 5.556 times 10 to the minus 10, okay? So I can put that in for KB, 5.556 times 10 to the minus 10 equals x. I'm just going to say x squared. I got to abbreviate this because my computer's not wanting to write. Over 0.250 minus x. So I plugged in everything from the equilibrium problem. So I'm going to assume that x is small, and I'm going to multiply both sides by 0.250 and take the square root. So I can say x is equal to the square root, we've done this 1,000 times, of 0.250 times 5.556 times 10 to the minus 10, which is equal to 1.7179 times 10 to the minus 5th, okay? And so you can divide that by 0.250 and multiply times 100 if you want to do the x is small approximation, and you get 0.47, showing that it's valid. But basically, this is my hydroxide ion concentration. So I'm going to skip the check there on that, check and see if it's valid. This is my hydroxide ion concentration. Okay, so I can get my POH is equal to negative log of the hydroxide ion concentration, which is 1.179 times 10 to the minus 5th, which is equal to, and they calculated it the other way, so I'm going to go ahead and calculate this, 1.179 exponent minus 5th, and I'm going to take the log of that. That gives me 4.928. And so the pH is going to be equal to 14 minus that. And that's going to be 9.07. Okay, so pH is 9.07. Okay, so moving on very, very quickly. I think that's our last math problem in this chapter. Let's just go on and finish up this chapter because we got to get done with it. All right, determining whether a cation is acidic or pH neutral. So kind of the opposite of the other thing. Okay, this is pyridinium cation is a conjugate acid of a weak base. Remember, pyridine was a weak base, and therefore it is a weak acid. So the conjugate acids of weak bases act as weak acids. So if we put this pyridinium cation in solution with something like a Cl minus, pyridinium chloride, then that's going to give us an acidic solution. Okay. The Ca2 plus cation is the counterion of a strong base and is therefore pH neutral, because remember, calcium hydroxide is a strong base, so the Ca2 plus is going to be pH neutral. Okay, the Cr3 plus cation is a small, highly charged metal, just like aluminum, and therefore, because it hydrates itself and it increases the H plus concentration, and it acts as a weak acid. So classify each cation as a weak acid or pH neutral. For practice 17.5, the lithium cation is the counterion of a strong base. Remember, lithium hydroxide is a strong base, so it's going to completely dissociate in water. Okay, and that means that's supposed to be a plus. Lithium plus OH minus, that means it's not going to want to go back in the reverse direction. So because of that, if you put lithium in solution like lithium chloride, okay, then the lithium chloride is going to completely dissociate. So it's not going to act as a base and pick up hydrogen from water and go back the other way and form lithium hydroxide. Methylammonium, if you put that in as a salt with something like chloride, okay, the methylammonium cation is the conjugate acid of a weak base, which would be methylamine. Therefore, this is going to be a weak acid. So if you put CH3 NH3 plus water. All right, water is HOH. Okay. What happens is it can donate a hydrogen to the water and it can form H3O plus the original base, which would have been methylamine. So because this is the conjugate acid of a weak base, methylamine, it's going to act as a weak acid by increasing the H3O plus concentration. So this iron, okay, is a small highly charged metal cation, and those act as weak acids. Okay. So the next problem, I think we got two more problems here. Determining the overall basicity of a salt or acidity of a salt solution. So again, this is kind of a recap for us. Strontium chloride. Strontium is the counterion of a strong base, strontium hydroxide, and is pH neutral. Okay, the chloride anion is the conjugate base of a strong acid and is pH neutral as well. Because remember, HCl is a strong acid, so that's going to completely dissociate in water. So if you put chloride in water, it's not going to want to pick up a hydrogen. It's not going to act as a base. The strontium is not going to want to act as a acid, so they are pH neutral. Okay, so if they are the conjugate bases and acids of strong acids and bases, they give us a pH neutral solution. Aluminum is a cation. It's a highly charged metal ion, and so therefore it acts as a weak acid. So aluminum is acidic. The bromide is pH neutral because remember HBr was a strong acid, so that's going to make bromide a pH neutral anion. So because the aluminum can act as an acidic forming cation, then we get an acidic solution. Okay. So the next one is ammonium nitrate. So the ammonium is, remember, the conjugate acid of a weak base, methylamine. So this is methylammonium, methylamine, and so therefore if it's the conjugate acid of a weak base, it's an acidic cation. The nitrate is the conjugate base of a weak acid, HNO3. I'm sorry, a strong acid, HNO3, and therefore it's going to completely dissociate. It's not going to want to act as a base, so this is going to not contribute anything, but so it'll be pH neutral, so we get an acidic solution. So that's going to be the major factor there. The sodium cation is the counterion of a strong base. That would be sodium hydroxide, right? So sodium hydroxide is a strong base, and since it completely dissociates in water, the sodium is not going to want to go back the other way. Okay, so that's not going to do anything to our solution. Formate is the conjugate base of a weak acid, formic acid, and therefore it's going to form a basic solution. So the overall solution will be basic. Now, if you have an acidic cation and a basic anion, then you have to look at their Ks in order to determine which is the bigger factor. Okay, so the Ka for ammonium, we have to actually solve for that because we don't have the Ka for ammonium, we have the Kb for ammonia. So if you solve for that, you get 5.6 times 10 to the minus 10. Okay, Kb for fluoride, we don't have the Kb, we have the Ka for HF. So you have to solve for Kb, and you get 1.5 times 10 to the minus 11. You see that the Ka for ammonium is greater than the Kb for fluoride, so the acid is going to trump the base in this case, so we get an acidic solution. Okay, so our 4 practice problems, we got like 7 minutes left. See if we can work these. The sodium bicarbonate is the sodium bicarbonate here. The sodium cation is the counter anion of a strong base, sodium hydroxide, so it's going to not contribute anything. It's going to be pH neutral. The bicarbonate, okay, is the conjugate base of a weak acid, and so therefore it's going to be basic. So this solution is going to be basic, okay. All right, and here we have ethyl ammonium chloride, and so ethyl ammonium is the conjugate acid of the weak base ethylamine, and the chloride is the conjugate base of the strong acid HCl. So the chloride doesn't contribute anything because HCl completely dissociates. So the ammonium is going to act as a conjugate acid of the weak base, and therefore the solution is going to be acidic, okay? KNO3, K is the conjugate, is the cation of potassium hydroxide. That's a strong base, so it's not going to contribute anything. The nitrate, the NO3, is the conjugate base of the strong acid HNO3, nitric acid. So the NO3 contributes nothing because both of those completely dissociate in solution. So this is going to be neutral, okay? Iron nitrate. Iron is a small highly charged cation, and so that's going to be a weak acid. The nitrate is the conjugate base of a strong acid, nitric acid, and therefore the nitrate contributes nothing. So the ammonium nitrate is going to be acidic. Okay. All right, so we have one more problem in this chapter. Oh, it is a math problem. I may have to work this math problem on Thursday, but I really just don't have time. Let me just run through this example here. All right, find the pH of an ascorbic acid solution. This has two ionizable hydrogens, and therefore you have to consider both of them. You have to consider what happens. But, well, the fact is this is not sulfuric acid, so the only one you need to consider is the first one. So you just look up the Ka for the first one, okay, and you solve an ice table. You set the Ka equal to the products over reactants, okay, and then you put the equilibrium values from the ice table in. We've done this 100 times, right? You set that equal to the Ka for the first ionizable hydrogen and solve for X, and that's going to give you your H plus concentration. You don't need to consider that second hydrogen that's left on there, this hydrogen right here, because this is not sulfuric acid. If it were sulfuric acid, you would have to consider it, and we're going to look at some of those in the next chapter. Okay, so when you solve for X, that gives you your H plus concentration. Okay, and so then you can get your pH from that, the negative log of the H plus, and that gives you 2.55. I got 4 minutes. Find the pH of a, guys, I guess I'm going to have to work this problem on Thursday. I will work this problem on Thursday because I do want you to understand how to do it. And I'm sorry I botched up so much today. I just think I just got mixed up at some point, and I will hopefully do better on Thursday. But I will work this problem, and then we're going to start chapter 18 on Thursday because this problem is not even significantly different. We're going to cover some of the same kind of problems in chapter 18. Okay, so do we have any questions before I let you go? Okay, I'm going to go ahead and let you go, and I will catch you on Thursday. We're going to start chapter 18. It's going to be more of the same.